there is no single temperature of space. Some regions of the universe are colder than the leftover radiation from the Big Bang. Others are so hot that atoms, atomic nuclei and even protons and neutrons can no longer exist. And at the very top of the scale is a theoretical temperature so extreme that our current understanding of physics begins to break down. Today we are climbing the complete temperature scale of the universe, from absolute zero to the hottest temperature that physics can describe. 0 to 2.7 Kelvin, the coldest end of the universe. We begin at 0 Kelvin, or minus 273.15 degrees Celsius. This is absolute zero, the lowest possible point on the conventional temperature scale. At absolute zero, a system has reached its minimum possible thermal energy. But despite decades of experiments, scientists have never managed to reach exactly 0 Kelvin. The laws of thermodynamics allow us to approach it but never completely arrive. The coldest known natural region in the universe is the Boomerang Nebula. Some of its rapidly expanding gas has cooled to approximately 1 Kelvin, or minus 272.15 degrees Celsius. This is even colder than the cosmic microwave background, the ancient radiation left behind by the early universe. That background radiation has a temperature of approximately 2.7 Kelvin, or minus 270.45 degrees Celsius. It reaches almost every part of the observable universe, but it does not mean that everything in space automatically has this temperature. An object's temperature also depends on the radiation it absorbs and the energy it produces. The Boomerang Nebula became colder than the cosmic background because its gas expanded extremely quickly. As the gas spread out, it lost energy and created a natural cosmic refrigerator. 10 to 100 Kelvin, the clouds between stars. At temperatures between 10 and 100 Kelvin, approximately minus 263 to minus 173 degrees Celsius, we find cold clouds of interstellar gas and dust. These clouds may appear inactive, but they are some of the most important structures in the universe. Inside their densest regions, gravity pulls gas and dust together. The cloud begins to collapse, its center becomes denser and hotter, and a new star can eventually be born. At these temperatures, many atoms can join together to form molecules. That is why astronomers often call these regions molecular clouds. The coldest parts of the universe are not always dead. Sometimes they are the places where new stars begin. 288 to 373 Kelvin, the temperatures we know. Now we reach the tiny part of the scale familiar to human beings. The average surface temperature of Earth is approximately 288 Kelvin, or 15 degrees Celsius. A comfortable room may be around 293 Kelvin, or 20 degrees Celsius. The human body maintains an internal temperature of approximately 310 Kelvin, or 37 degrees Celsius. At normal atmospheric pressure, water boils at 373 Kelvin, or 100 degrees Celsius. To us, the difference between freezing water and boiling water feels enormous. But on the complete temperature scale of the universe, this entire range is almost invisible. We have barely moved away from absolute zero. Thousands of Kelvin, the surfaces of stars. At several thousand Kelvin, matter begins to glow brightly. Relatively cool red stars can have surface temperatures near 2,500 to 3,500 Kelvin, or approximately 2,200 to 3,200 degrees Celsius. The visible surface of the Sun is about 5,800 Kelvin, which is roughly 5,500 degrees Celsius. Hot blue stars can exceed 30,000 Kelvin, or approximately 29,700 degrees Celsius. The color of a star is therefore connected to its temperature. Cooler stars appear red or orange, while the hottest stars shine blue-white. But even the hottest stellar surface is still cool compared with what lies above it. Millions of Kelvin, stellar atmospheres. The outer atmosphere of the Sun, known as the corona, can reach approximately 1 to 2 million Kelvin. That is roughly 1 to 2 million degrees Celsius. At such enormous temperatures, subtracting 273 degrees makes almost no practical difference. Strangely, the corona is much hotter than the visible surface beneath it. Scientists continue studying exactly how magnetic fields and waves transfer enough energy into this thin outer atmosphere to produce such extreme temperatures. Hot gas between galaxies can also reach hundreds of thousands or millions of Kelvin. However, this gas is so incredibly thin that it would not feel like standing inside a fire. There may be too few particles nearby to transfer a significant amount of heat to you. Temperature tells us how energetic individual particles are. It does not tell us how many particles are present. 15 million Kelvin, the core of the Sun. Deep inside the Sun, the temperature rises to approximately 15 million Kelvin, almost 15 million degrees Celsius. Under enormous pressure, hydrogen nuclei move fast enough to overcome their electrical repulsion and fuse together. This nuclear fusion creates helium and releases the energy that eventually reaches the surface as sunlight. But even the center of the sun is far from the hottest environment in the universe. It is only the beginning of the truly extreme part of the scale. Billions of Kelvin, supernovae. When a massive star runs out of nuclear fuel, its core can collapse in less than a second. The collapsing material is compressed to extraordinary densities, and temperatures can rise to billions of Kelvin, approximately the same number in degrees Celsius. At around 10 billion Kelvin or about 10 billion degrees Celsius, ordinary atoms cannot exist. Their electrons have long since been separated, and even atomic nuclei can be broken apart by extremely energetic radiation. These conditions help create a neutron star and drive one of the most powerful explosions in the universe, a supernova. For a brief moment, the death of one star can produce more light than an entire galaxy. But even a supernova is thousands of times colder than the next level. Trillions of Kelvin, Quark-gluon plasma. At temperatures of several trillion Kelvin, or several trillion degrees Celsius, protons and neutrons can no longer maintain their normal structure. They effectively melt into their fundamental components, quarks and gluons. This creates a state of matter known as quark-gluon plasma. Scientists have produced tiny droplets of this material by colliding heavy atomic nuclei at nearly the speed of light. Experiments at the relativistic heavy ion collider have created matter at temperatures of several trillion degrees. Similar conditions existed naturally only during the first microseconds after the Big Bang. At this point, we have passed the temperature of stars, supernovas, and almost every object that currently exists. But an enormous unexplored gap still remains. 1.4 times 10 to the power of 32 Kelvin, the Planck temperature. The Planck temperature is approximately 1.4 times 10 to the power of 32 Kelvin. Written out, that is a 1 followed by 32 digits. In degrees Celsius, the number is essentially identical because subtracting 273 from a number this large changes almost nothing. The Planck temperature should not be treated as a confirmed wall that can never be crossed. It is better understood as the point where our existing theories stop being sufficient. At this scale, quantum physics and gravity would both become critically important. General relativity describes gravity, while quantum mechanics describes the smallest particles. But we still do not have a complete theory that successfully combines them under such extreme conditions. The universe may have approached this temperature during the unimaginably brief Planck epoch immediately after the beginning of cosmic expansion. We cannot recreate these conditions, and our current equations cannot reliably tell us exactly what happened there. The top of the temperature scale is therefore not simply the hottest fire imaginable. It is the boundary of known physics. The end of the scale. Temperature determines what matter can become. At low temperatures, atoms can form molecules, clouds, and eventually stars. At extreme temperatures, even protons and neutrons lose their familiar structure. And at approximately 10 to the power of 32 Kelvin, the scale ends, not because we know that nothing hotter can exist, but because our physics can no longer describe what happens next. That is where temperature stops being just a number and becomes one of the greatest mysteries in the universe. Thanks for watching, and I'll see you next time.